In this program, we're going to show you some very interesting experiments, and they're especially interesting because they appear to lead to quite contradictory conclusions. In fact, it took some of the world's best physicists quite a long time to work out just what these experiments mean. And in the process, a new theory was born, quantum theory, which not only revolutionized physics, but also became the basis for such things as nuclear power and transistors. So, let's start by having a look at this apparatus here. You've seen it before, of course, because it was in the TV part of Unit 9. This is a laser, and I'll just switch it on. Yeah? And this is a diffraction grating, very much like the one you would have used in the home experiment of Unit 9 or in the physics experiment at the summer school. Now, what do you think will happen if I take the diffraction grating and put it into the laser beam? Well, I'm sure you expected that. A row of diffraction maxima on the screen, bright spots, and remember, of course, that the spacing between those spots depends upon the wavelength. Notice also that if I tilt the grating one way or the other way, the pattern also changes its orientation. Now, I can take another grating, just the same as the first one, stick the two together at right angles to each other, so as to make a two-dimensional diffraction grating. And now what do you expect to see? Oh. Get it nicely in the beam. Yeah, there we are. Well, a two-dimensional diffraction pattern. And the orientation of the pattern, again, of course, corresponds to the orientation of the two-dimensional grating. Now, naturally, we could extend this idea to 3 dimensions, and then we'd be simulating a 3-dimensional periodic structure, rather like the sort of thing you get with a crystal, in which the atoms are arranged in a regularly repeating pattern in 3 dimensions. Now, if instead of having just a single orientation like that of a 2-dimensional grating, what do you think would happen if we had not just one orientation, but lots and lots and lots of them with all different random orientations, like that? Well, let's see if we can show what would happen. Okay, what I've got here is 2 gratings crossed over each other just as I had before, except I put them on this little disc, you see, which can rotate. And as it rotates, of course, the 2 gratings take up every possible position, and so the spots, the pattern on the screen, can take up a whole lot of different positions. And if I switch this little motor on, yeah, now I think if we just take the lights down a little bit, you'll be able to see that a bit more clearly. Well, there you are. Isn't that beautiful? Now, remember that the spacing between the spots depends on the wavelength, and so also the radius of these diffraction rings, which are made up of the spots, will depend upon the wavelength.
Well, these rings are very similar to what Mike has. But what are we dealing with here? Let's start off with something a little simpler. This is a cathode ray tube, rather similar to the one in your television set. And at this end, we've got an electron gun. I can show this best with this duplicate set here. This is the heated cathode, and that emits the electrons. This is a plate which can be charged up to a high voltage, several thousand volts, and that means that the electrons get accelerated from the cathode along here, and they come out of that hole at the end there. They come out in the form of a fine pencil beam, and they go shooting across this evacuated tube, and the reason it's evacuated is that we want to cut down the collisions with the air molecules, and then the electrons strike this fluorescent screen and give rise to this spot. Now I can demonstrate that we are really dealing with electrons by bringing up this magnet. As you can see, we can move the spot around because the electron beam consists of moving charged particles, and these trajectories are affected by a magnet. So what's the difference between this tube and this one over here? Well, the difference is this. It's a tiny thin foil of graphite. And this is placed inside the tube. It's placed over the exit point of the electron gun. So when the electrons come out of the gun, they have to pass through the target in order to get to the screen. And that's what gives rise to this pattern. Now, it looks like a diffraction pattern, but you know that in order to get such a thing, two conditions have to be satisfied. First of all, we have to have a random array of cross gratings, and we also need some radiation that has a well-defined wavelength. Well, it's not difficult to see how the first condition is satisfied, because graphite has a crystalline structure. It consists of these regular arrays of atoms, all in a line, and indeed we can draw a set of parallel lines through them, as you can see here, with equal spacings, so that would constitute a grating. And moreover, these same atoms belong to other sets of straight lines, like this one here, and so it actually is a cross grating. And with that foil of graphite, we have a great many very tiny crystals, so we get a random array of cross gratings. So if this is a diffraction pattern, then it means that the electron beam has to have a wave-like nature as it passes through that target. It has to have a wavelength. And we can actually measure the wavelength by measuring the diameter of the rings and by knowing what the spacing of the atoms is. Now I want to show you something interesting about this pattern and the wavelength of electrons. You remember I said that the electrons were accelerated by that high voltage plate. Well, with this device here, I can adjust the voltage and therefore adjust the energy of the electrons. So as I change the voltage on that plate, I want you to observe what happens to the diffraction pattern. I think it's probably best if you concentrate on one of those rings in particular. So here we go, starting off at about 2.4 kilovolts and going down. That's 2.0, 1.5, and down to 1.0 kilovolts. As you see, the pattern gets larger the smaller the voltage. Let's just go back up again, give you a chance to see that again. Going up now, back up to 1.5, 2.0, and finally 2.4 kilovolts again. Okay, so as the voltage goes up, the pattern goes down, which means that the wavelength is decreasing as the voltage goes up. And so it turns out that there is a very simple relationship which connects the wavelength with the energy of the electrons. Actually, one uses the momentum, and this is the relation. It's called the de Broglie relation. It connects the wavelength lambda with the momentum p, and the connection is made via Planck's constant h.
Perhaps it surprised you just a bit to see electrons behaving like waves. But were these diffraction patterns really produced by electrons? Well, there's one surefire way of checking that. We're deflecting the electron beam after it's come through the graphite target with a magnet. So the electron beam is interacting with the magnet, behaving like particles. So in the same piece of equipment, we've demonstrated both wave behavior and particle behavior. Now, if electrons really are particles, then they ought, like any respectable particle does, to behave in a certain way when they have collisions.
In collisions, there's a moment of impact during which there's an exchange of energy. And that takes place according to the law of conservation of energy, which says that the total energy before the collision is the same as it is after. Now, if electrons behave like particles, as well as like waves, then we would expect them to exhibit this kind of behavior. Now, of course, it's very difficult, in fact, it's impossible to observe an individual electron directly because it's very tiny. But there's something we can do. We can use a device called a bubble chamber. Now that is a device where you have a tank of liquid, transparent liquid, under special conditions of temperature and pressure. And what we do is we fire the electron into the tank, and as it goes through the liquid, it gives rise to a trail of bubbles, and these very rapidly grow to a visible size, whereupon a light is flashed, and that allows a photograph to be taken. So that provides a permanent record of where the electron went. Well, now you're looking at an actual bubble chamber photograph of an electron track. And if we follow it along, we find that at this point here, it seems to split up into two tracks. Well, what actually happens at this point is that the incident electron strikes a stationary electron belonging to an atom of the liquid. And the incident electron then careers off like that, and the other one recoils off in this direction. Now you'll notice that these tracks are not straight, they're curved, and that's because on the bubble chamber there's a magnetic field applied. And that has the same effect as that toy magnet we were using over there with the electron beam in the tube. The magnetic field on bubble chamber causes these tracks to curve. And the idea of that is that the more energetic the electron, the harder it is for the field to curve them. So by measuring the curvature of these tracks up here close to the collision point, we're able to make an estimate of the energy of the electrons. And when this is done, it turns out that the exchange of energy in that collision takes place according to the law of conservation of energy, just like those ball bearings.
So now we've got two experiments to interpret. In the first one, the electrons were diffracted by those graphite crystals, and they were behaving like waves. And in the second one, with the collisions, we had electrons transferring energy from one to another and behaving like particles. Now, you shouldn't be too surprised to find electrons behaving both like particles and like waves, because after all, you've come across this sort of thing before, this wave-particle duality in Unit 9, but then it was with light and not electrons. Now, perhaps you remember Keith Hodgkinson demonstrating the particle properties of light using this gold leaf electroscope. What he did, remember, was to charge up the electroscope, then he brought up an ultraviolet lamp and shone the ultraviolet straight onto the top of the metal plate. And you can see the electroscope discharged. Now, those experiments with the photoelectric effect clearly demonstrated that light interacts with matter in a way which leads us to suggest that light has particle properties. It transfers energy in lumps or in quanta when it interacts with matter. But if light, or for that matter, or electrons, really are particles, then as well as energy, they have to have another property, and that's momentum. And when they collide, they need to transfer momentum. Well, do photons really have momentum?
In order to answer that question, we have to take a closer look at these collisions between these balls. In particular, I want you to note this time that after the collision, the incident ball is deflected through an angle. Right, now what we need to do is to see how the energy of the deflected ball depends upon the angle of scatter. And in order to show this, what I've done actually is to record quite a number of these collisions, and I'm going to show them to you in slow motion. Right, well, let's begin with the simplest of all collisions, this one, where in fact they miss, and the ball just carries straight on with a deflection angle of 0, and it carries on with its original energy. Right, now this time let's hope they hit. A very small deflection angle, and as you can see, the ball carries on with almost its original energy. It just loses a little bit. Now what's going to happen? Right, well, a much larger scattering angle, and now you'll notice that there really was a big change in the energy. And finally, let's try an almost head-on collision. Well, there you see the change of energy was very obvious indeed. So what we see from those is that the bigger the angle of deflection, the smaller the energy of your incident particle afterwards. Now that correlation has got nothing to do with the conservation law of energy. That says nothing about angles. Now what is happening in these collisions is that not only is energy being conserved, but something else is going on there. We're having conservation of momentum. So that really is the clue for finding out whether photons carry momentum. We investigate it by seeing whether there is a correlation between the energy of the scattered photon and its angle of deflection. Now, a few days ago, I went along to Warwick University, where they have a piece of equipment there which will allow us to investigate this. This is a radioactive source. It emits gamma rays, which is a high-frequency form of light. I'm just putting it into this lead block, which has got a small hole on the other side. So the idea is that the gamma rays come through that hole in the form of quite a narrow beam. Now this is a detector of gamma rays, so what I'll do is I'll start off by simply placing the source directly opposite. So from here, the gamma rays go straight through and into the detector. Now we can see what the detector is picking up on this screen. What we're doing is we're plotting the energy of the detected photon along here against their number. And as you can see, all the photons are bunched here around this unique energy of 60 keV, which happens to be the energy you expect for photons from this radioactive source. Now what we're really interested in, of course, is scattered photons. So what I'll do is turn this round like that, and then we put in a target. So now the gamma rays come along here into the target where they strike electrons, and in order to get into the detector, they have to go along a path like that. So they have to scatter through 55 degrees. Now in this position, the display we have is this. On the right-hand side, we've still got that same peak we had before, but now you see it's accompanied by a second peak, which corresponds to the scattered photons. It's at a lower energy, which of course is what we expect from the law of conservation of energy. But the really interesting thing about that display is that the scattered photons are in the form of a narrow peak. In fact, that peak is consistent with the scattered photons having a unique energy, an energy corresponding to this particular angle. And that certainly is one of the features one expects if the photons carry momentum. But in order to really clinch it, we have to try out different angles. So let me just swing it round like this. And from here, the gamma rays have to scatter through 90 degrees to get into the detector. So let's see what the screen says now. Well, we now have our new peak, and you'll see that it's at a still lower energy, corresponding to the larger angle. And that, of course, is exactly what we wanted from the ball bearings, a lower energy corresponding to a wider angle. And finally, let's try the largest angle that I can manage here, just like that. And now the gamma rays have to go through 155 degrees to get into the detector. And this is the result, a yet lower energy. We can understand these results in a quantitative fashion if we assign to the photons not only an energy, but also a momentum P given by this expression. P equals the energy of the photon, E, divided by the speed of light, c. Now, of course, we know that the energy of a photon can be written h times f, h being Planck's constant and f the frequency, and so we can write it like that. Moreover, we know that f over c is 1 over lambda. So we can write p as being h divided by lambda. Or if we take lambda, the wavelength onto the other side, we eventually end up with lambda equals h over p.
So this equation, the de Broglie equation, links the wave properties to the particle properties, both of electrons and of photons. Remember, the wavelength, lambda, has to be, of course, a wave property. P, the momentum, is a particle property, and the two are linked via Planck's constant. So we can use a wave model or a particle model to describe the way in which electrons or photons behave. The wave model is the one to use to describe where the radiation goes, the angles at which you'll find diffraction maxima, for example, whereas the particle model is the one to use to describe how radiation interacts with matter, the emission of photons from atoms, for instance, or the absorption of photons by a metal surface.
One final point. This is the setup that Mike began the program with the laser, the diffraction slits, and the screen showing the diffraction pattern. We've learnt that the wave model tells us how much light is going to fall on various parts of the screen, and the particle model tells us how the light will interact with the atoms of the screen once it gets there. But let's suppose, just suppose, that we were dealing with a laser which gave out an extremely weak beam of light. So weak that the amount of energy between here and here at any one time corresponded to, let's say, 1 photon's worth. Now, what conceivable meaning can we assign to a diffraction pattern when we're only dealing with a single photon? Well, suppose we did have such a setup. This is the kind of thing we would find on the screen. We get individual photons still arriving, but at first there's no sign of a diffraction pattern. It's only after a while that we begin to realize that those photons aren't arriving just anywhere, they're arriving at regularly spaced places. And so it is with time, we gradually begin to discern the diffraction pattern being built up. So really what's happening there is that the diffraction pattern is governing the probability of the photon arriving at various places on the screen. In some regions the probability is high, and in others it's very low. So in this program, when we've been talking about waves, what we've actually been talking about are probability waves. And this idea is developed further in the main text.